me share my screen. Can everybody see my slides?
Yes.
Okay, thank you. So today I'd like to welcome you to the workshop on performance tools for emerging exascale platforms, status and challenges. I'm John Mellor-Crummy, a faculty member at Rice University, and other people that are participating in the breakout session are Samir Shende from the University of Oregon, Heike Jagode from
Started
University
a couple
of
of minutes ago.
and also Anthony Danalis from University of Tennessee, Knoxville. So we'll have three talks. The first talk is going to be given by Samir Shende. The second talk is going to be a tag team talk by Heike Jagode and Anthony Danalis. And the last talk will be given by myself. So in this session, we're going to talk about the Tau performance system, the PAPI library for accessing performance counters on CPUs and GPUs, and HPCToolkit. So the format for this breakout session is going to be 3 30-minute talks, and there should be some time for questions at the end of each of these talks. And then we'll have some additional time for additional questions and discussion at the end. And so just before we get started, I wanted to show one more slide saying that we have a lot of challenges in building tools for these emerging supercomputers. And so there's complex CPUs with deep memory hierarchies. There are multiple GPUs with different characteristics on the different systems. We've been trying to cope with NVIDIA GPUs, with Intel GPUs, with AMD GPUs. They have different hardware characteristics, different programming models, different software stacks. The software stacks are pretty intricate and quite different across the vendors. And so all of these things present significant challenges that make it difficult for us to build tools. And so this has really been a collaborative effort with the vendors, and the collaboration's not over. We're still waiting for some pieces from them. And so this is all about ongoing work. So in addition to the difficulty of dealing with the software stacks and the hardware, another challenge that we face is measurement and analysis at scale. And so this is something that we have to tackle in our tools if we're going to be able to run applications and measure them at significant scale on these exascale systems. And then finally, a role of our tools is to attribute performance back to the source code and to try and provide some actionable feedback so you can know where to tune and what to tune in your code. And so without any further ado, I'd like to turn things over to Samir, who's going to give the first presentation about the Tau performance system.
John, while you're changing this is your official ECP bouncer, who is the volunteer for this session. If you have not renamed yourself to a full name, first and last, you will be bounced from the session. So please do rename yourself.
How do you do that?
In the participants tab, you can select, you can say show participants and then select yourself and then hit rename.
Correct.
Under the, if you put your name there, it'll say more. Click on more, and it should say rename.
Okay, Samir, you can go ahead.
Scott has a question. Scott?
Sorry, I was in a mode and I hit the question thing by accident. I apologize.
Okay, no problem. So thank you for inviting me today. This is a joint work with the team at the University of Oregon and ParaTools. And I'll speak about what challenges we are facing in the Tau performance system, where we are in our support for the various GPUs. And it's getting harder and harder to accurately measure and optimize the performance of our codes with growing hardware complexity, the Tau performance system aims to deliver a scalable, portable performance evaluation toolkit for not only HPC, but also AI ML workloads. And let me just start off by talking about the status of Tau on the AMD platforms in support for the MI100 and MI250X GPUs. Tau is an integrated performance toolkit. It has instrumentation support, measurement, analysis, visualization tools that all work on these systems. We support the AMD CPUs as well as GPUs. And with ROCm, we have gone through various versions of ROCm. We are currently in support of ROCm 5.1.0, and it supports the HIP, OpenCL, ROCm, the Hpc compiler, and also the ROC profiler and ROC tracer interfaces. I'll speak a little bit more about what that entails. We also support PAPI and liquid hardware performance counter libraries. It supports event-based sampling and direct instrumentation modes, which allow us to see the performance at the function, loop, statement level, even at the file level. And we have support for compiler-based instrumentation using Hpcc compilers on the host side. And also we have created a new plugin, an LLVM plugin that allows us to cherry pick the functions that we want to select for compiler-based instrumentation. And this works with Clang, Clang++ compilers, as well as the Hpcc compilers. We have tools for analysis, including Paraprof, which has a 3D profile browser. We have Perf Explorer for cross-experiment analysis and data mining. And we also have Chrome and Perfecto.dev tools for trace visualization. Tau also ships the JumpShot tool for trace visualization. And we also work closely with the Vampire team at the TU Dresden in Germany, which is Vampire is a commercial trace visualizer that uses the OTF2 or the open trace format output that Tau can generate. So the update for AMD, we have support for ROCm 5.1.0. Now we support both the ROC profiler and ROC tracer interfaces in Tau. Now we found that in getting the events from ROC profiler, we were seeing that the pairs of start-stop events, which typically characterize the entry and exit of a kernel, these records, these pairs of records were not coming in an order which is monotonically increasing in time. So closer to the end of the execution, we may find a event that actually belongs to the near the beginning of the execution. So Tau supports both profiling and tracing modes of measurement. With profiling, we take the difference between the stop time and the start time to calculate the total time in that kernel. And that works fine with the generation of profile files, even if we get the pairs of events later. Now, Tau has a way of creating a ghost thread, which is managed by the host side, where we receive the events coming from ROC profiler that says the kernel A executed from time T1 to time T2. And then we can take the difference, T2 minus T1, and calculate the total time spent in that kernel A and attribute it accordingly on that particular GPU queue. But we found that for generating traces and timestamped event logs that are monotonically increasing, you cannot get a pair of events later in execution that belong to the beginning. So we created a sliding window algorithm where we would not commit the trace file to the stable IO. We would just store it in the memory for a few records. And we found that by experimentation, a good length was about 128,000 records that we could store in memory before committing it to the disk. And then if you, within this window, if you get an event that should be earlier in the window, then we basically move it to the exact point where it should be and then commit the trace. So there's a moving window algorithm that we implemented to take care of this out of order pairs of events that we were getting from ROC profiler. And so this is shipping now in Tau version 231.1 beta 3. It's available from our Tau releases webpage. And Tau is also integrated with E4S in a Singularity container that you can download from the e4s.io webpage. We have support for compiler-based instrumentation with Hpcc, and we have created a LLVM plugin for Hpcc for selective instrumentation. This allows you to specify a selective instrumentation file which has either an include list or an exclude list of functions. If you say an include list, it could look something like this, where you say, I want main, I want functions F1 through F5, but nothing else. And then the compiler-based instrumentation will just cherry pick these functions and instrument them. If you have an exclude list, it could say something like exclude these functions like foo and bar and instrument everything else. Now, why do we need this? We need this because in C, while this may work well with C to instrument everything, with C++ codes, even if you include like a vector STL, standard C++ header file, you get hundreds and thousands of these functions that are constructors and destructors. And if you try to instrument every entry and exit, you may incur excessive overhead. We recommend event-based sampling for those cases in C++, but this is a powerful capability for C++ codes. And we have to be careful while instrumenting it. You see, we get the entry-exit records from the kernel on the GPU side using the rock profiler or rock tracer interfaces. So we don't need any instrumentation there, but the host side functions do need this, even if we are using the Hpcc compiler. But we have to be careful to identify in the intermediate representation if a function is bound for the GPU. And if it is, then we avoid adding the start-stop hooks to those functions by doing an intelligent instrumentation pass by examining the intermediate representation, the IR of the LLVM. So we need this plugin to be loaded by the compiler while it is doing the code generation, and then for it to selectively instrument the code based on what the user has specified, and by examining where that function is going to execute, whether it's on the CPU side or the GPU side. So this is now stable. We had some issues with the compiler toolchain, and the problem was that the Hpcc compiler could take an argument for a plugin. The LLVM F legacy pass manager option could allow you to pass the selective instrumentation file as a parameter. But there was a bug in Hpcc compiler. And the bug was something like this. Passing an argument to a plugin works if you are compiling a C file. But if you are compiling a C++ file, it does not work in the current implementation. So we worked with the AMD compilers team, and we raised a bug report. But the problem is that even if you do have a fix for this bug, which comes in a future version of Hpcc, what do you do with all the installations? People would have Hpcc 5.0.2 or 5.10 already installed, and you cannot ask them to upgrade to the latest version, which is bug-free, just to support this. So what we did is we experimented with an environment variable. We said, what if we don't have to pass the plugin, the selective instrumentation file name, but we pass it through an environment variable that the user sets, and that variable is called tau compiler select file. And you can then pick up the file name from that selective instrumentation file and avoid the passing of an argument to the plugin. And so we have this working. We have tested it with multiple versions of ROCm and the Hpcc compiler, and it's stable. It will be released very soon in the Tau 2.31. But if you want to try it, it's there right now on the website and also on our GitHub page. So you can specify the Tau compiler select file environment variable to specify where the selective instrumentation file resides. And then it will do the instrumentation at the compiler IR level. Now we have support in Tau for OpenMP tools interface on the CPU side with the OMPT 5.0. And we are exploring the tau support for OpenMP GPU offloading, the target offloading options with the OpenMP tools interface. We already have this support shipping in Apex, which is the asynchronous runtime support for in tau. The Apex measurement system, Kevin is the lead author on that. And we can generate profiles as well as traces. I just wanted to show you that this is how a application profile with OpenMP target looks in tau. For a simple example, coming through the Apex runtime. And here is the perfetto.dev, the trace visualizer, where you can zoom into a particular portion of the timeline and you can see the target compute and region initialize directives. This soon will be a capability that tau supports natively as well. So you don't have to go directly through Apex, but it is available now and it's working on the AMD GPUs. You can compile the program with the FOpenMP with the target x86 64 PC Linux GNU with the AMD GCN, AMD HSA, and these OpenMP target flags. Here I'm just using it for the architecture of MI100 with the GFX 908, but it will also work on GFX 90A. And then you use these options to compile the program, and then you launch it with Apex to generate these trace files, and that you can visualize, and you can see all the events over here for the OpenMP target directives. So this is a capability that will be shipping in 231.1 soon, and we have support now in tau to not only use the prog-n supplied compilers, but to use Hpcc or Clang with the environment which provides the MPI. And this required quite a bit of tooling in the case of tau, where we had to say, don't use the compiler from the prog and cray, use Hpcc, because that's the one that understands the Hp constructs. And whether it is prog and cray or AMD or MVAPIC, we can now specify that compiler. That's not saying that the progams are up to the point of supporting ROCm 5.10. They have support for 4.3, but they are moving in that way that we will soon have a prog and cray or prog and AMD that works seamlessly with ROCm 5.10. We also have support for MVAPIC2, so you can have MVAPIC2 configured with Hpcc using tau. So you pick the MPI from these and pick the Hpcc compiler from here. I just wish there was a little better integration, because you have to go through many hoops to be able to compile these codes with Hp and MPI. So typically we say MPI options, we have to add some options. We have to check these environment variables like PE, MPH, GTL directory, and get the -i-l options for MPI to compile them. If it's not using this, if you're using the MPI CC scripts from cray, you have to make sure that you get the special MPH prefix bin directory to get the MPI options, and then the MPI CC show to parse those to get the libraries and include files. So I wish we didn't have to do all this, and it was a easier lift for integrating the MPI with different compilers. I wish we had a script which just worked with the MPI from this. And we would be able to use the HIP compilers more seamlessly with the programs. There's a question about using compiler-based instrumentation and using the ROCm ROC profiler together. So we need to have some knowledge about timer names without having to resolve addresses from the samples. And we can, as Kevin mentions over here, having both the support from rock profiler as well as compiler-based instrumentation can be more powerful in some cases. We also have hooks for other tools. We have support for Coco's profiling interface. So if your code is using, for instance, if you are using Trilinos and it uses Cocos internally, then you can use Tau to get access to the entry and exit routines for, say, Cocos parallel for or parallel scan or parallel reduce, etc. We also have support for OpenACC profiling interface. And I spoke about OpenMP, but we have support for other runtimes, including CUDA, HIP, OneAPI. And in those cases, we don't need to actually use the compiler-based instrumentation at all. We can just use Tau exec as a tool to launch the execution and then get all the events at the entry and exit of those pointers. And as I mentioned, that C++ instrumentation with just instrumenting everything is far too invasive, and a hybrid approach can be better with the plugin and the event-based sampling. PDT or the source instrumentation still works properly for Fortran and C. And you can specify this using the compiler select file, as I mentioned. And it checks if the function is being sent to the GPU by examining the intermediate representation. We have tested it with some ECP applications like these, the Co-HHM and AMG, but we are doing some more work before we do this release. Now, with Rock Profiler, we also have some metrics that are available through Tau, and you can specify the Tau metrics environment variable. You can say Tau metrics is time and PAPI native event, and PAPI native avail will show you the list of events that are available, and then you can use this prefix called PAPI underscore native and underscore, and then the full name that's provided by the PAPI native avail output. And the counter support is something that I'm sure AMD has heard a earful of, and there are a lot of things that I'm sure that will be covered in the PAPI talk, where their tool called MIPerf has some counters that are not available widely yet, but it's encouraging to hear that AMD is going to make those counters available, and that soon we will be able to have a much richer set of hardware performance counters that will be available through Tau, through these interfaces. And in particular, we are looking forward to getting access to the level 1 data cache misses and flop rates and the flop counts that will be available. And I hear from Phil that L1 and flop counters are now visible on Crusher, and that's very encouraging. We need to do some more testing with that and see how PAPI can provide access to those counters, and we'll be able to read those. And Phil, feel free to unmute yourself. Is this available through the ROCm 5.10 release that's there on Crusher, or is there a separate module that you have to use for getting access to these counters?
So it was a pre-release XML file that AMD provided that OLCF has put on that system. It's going to be in the next release by default, but we've essentially backported it. So if you wanted to use ROCm 5.1, you should be able to see those counters. That's
great. And AMD has been so reactive to our requests, whether it's with compilers or with hardware performance counters. We couldn't do all of this integration without their support. Really happy to hear that these counters are now accessible through this XML file that Phil mentioned. If you would kindly just send us the location of this XML file, we'll appreciate it.
Samir, actually, we are just almost about to finish because of rushing. By Friday, everything will be clear up, because basically we only on validation. We may give all of the counters immediately, but they're not 100% validated, and we have 5% remaining, and hopefully tomorrow will be finished. and XML file is ready because it was just given to it's on the crusher, and so we have like I'll check with on the NDA we may release it now, but afterwards like formal actions you can use it will be posted on GitHub.
That's
XML
great.
file.
Like I said, the cooperation with AMD has been phenomenal, and thank you for accepting all of our requests like this. And I'm sure the PAPI folks are thrilled to find that we will be able to get access to these counters.
Yeah, this morning I have already thread on communicating. Giuseppe from PAPI team, he just working with our guys to resolve the issue of incorrect reading of some counters, because this is like a problem, and it's on PAPI component problem. We're just fixing it.
And we really appreciate your support for giving hardware and software updates to the partners. AMD has taken such a proactive role, and they need to be commended for this, for their support for tools community. And as I mentioned, that we have support for OpenMP tools interface with OMPT offload events with Apex already, and we soon hope to have this support in Tau as well. As I was showing over here with the Perfecto API, and these are the OpenMP target clauses. Here is the image that shows you how the regular GPU support looks with the Apex gtrace option. And you can get this from the perfecto.dev, which is the newer version of the Chrome //tracing API that's there in the Chrome browser. And here is the GPU support with Tau with OTF2, which can be visualized with the Vampire trace visualizer. And a number of DOE sites already have licenses for Vampire. Oak Ridge has a limited license, but Sandia, Los Alamos National Labs, and Livermore, all three have licenses for Vampire and Vampire Server. And so it's very easy to get access to this tool. It's a commercial trace visualizer, but what is interesting is when you specify OTF2 and run an uninstrumented application with Tau, there is no need for further merging or conversion of the traces. You can immediately launch the Vampire tool and access the trace file because Tau generates the OTF2 traces natively. There are other tools that also generate OTF2 files, including Scorpy, and other tools are also looking at this as a standard output format. And Tau support for Intel's One API includes support for DPC++, C++, C, Fortran, compiler-based instrumentation, source-based instrumentation. There is support for F-instrument functions option. We have support for the OpenMP tools interface, but we have not yet released, as I mentioned, the support for OMPT offload directives yet. That's still work in progress. Level 0 integration is there with DPC++ runtime event, so you can see exactly what the GPU runtime is doing. There is support for DPC++ symbol demangling, OpenCL performance instrumentation, MPI profiling interface with Intel HPCToolkit, Python support, and Macau binary instrumentation, pin integration, and of course, PAPI and Liquid performance counter library integration. So Intel also has a number of rich interfaces for instrumentation at the above levels for transparently observing the key events. And you do not need to change the source code or the binary in any way. You can just run it with Tau in this manner. Some of the challenges that we faced was that we were trying to do support for the plugin, LLVM plugin, and the DPC++ compiler is based on LLVM, but they are missing some key points which makes it harder, or should I say impossible, to actually load any LLVM plugin currently in the DPC++ compiler. They are aware of this, and we have told them about this and reported this as a bug. But DPC++ currently does not support external plugins. Even if you are able to build the plugin by not taking the LLVM.CMake from the One API, but from an equivalent toolchain, while loading a plugin, it crashes the compiler, which it should not. And so they are going to fix this in a future version of DPC++. We do have support for libdrm, devel, and level 0 packages. We are looking at how we can use this with SPAC, and there is work going on right now for a level 0 package that will be integrated, and that will make it easier. Right now, we can use the SPAC --dirty flag when you say SPAC install tau with the --dirty, and it can query the LD library path, which normally SPAC zaps out, and then find out the exact location of the level 0 package and configure it. So that works, or you can specify in a packages.yaml file the full path to the location of level 0, and that also works to pass it to the tau script. And okay, Phil just said that it's not there with 510, but it will. They will apply that patch. And of course, MPI support is now stable with Intel GPUs as well. Tau supports CUDA, NVHPC, Cocos, OpenCL on NVIDIA GPUs. We have CUPTI metric support, where you can specify the CUPTI option for tau exec and set the tau metrics environment variable. We have some preliminary code for doing sampling on the GPU itself, and there's an output in a CSV format file, SAS. And then we have support for NVIDIA GPUs on all 3 architectures, including ARM64 and IBM Power 9, PPC64LE or Summit with x86 64 as well. And we have support for uniform memory, so you can see the events from host and the GPU side using the same memory. And we have support for Prog and Cray and NVIDIA on HPC and Cray systems. And we hope to have the OMPT target offload directive support that's currently available in Apex. So to recap, Tau supports a number of runtimes, including MPI, pthread, OpenMP, OpenACC, and OpenCL, CUDA, Level 0, ROCm, Cocos, and Python. And you don't need to change anything in your code. You can just launch it with the Tau exec or Tau Python code. And you can even mix and match this. So you can have Rock Profiler with MPI, you can have Cocos with pthread with MPI, or you get the idea. You can mix and match this. And this is how you launch it. You specify a tag such as Rock Profiler or Rock Tracer with the -ROCm for AMD GPUs, L0 for Intel, CUPTI with the -UM optionally for uniform memory access, OpenCL, OpenACC, IO, OpenMP tools interface, OMPT, memory, and event-based sampling at the file, function, or line level. And there are environment variables that you can set. I'm not going to go into this in detail right now. This is how you install Tau on your laptops. And you can use Tau with SPAC, which is the basis for the E4S software. You can just say SPAC install Tau, or you can say Tau version 2.31 with compiler GCC version 930, which it gets from the SPAC compiler find command, or with plus ROCm or plus level 0 or OpenCL or MPI. And SPAC is a great package manager, and its community is growing rapidly. Please visit the spac.io webpage. There are also tutorials at the ECP annual meeting. And E4S is curated SPAC-based software distribution, which targets all these platforms and has containers with pre-built binaries of products, including Tau, available on Docker Hub and E4S website, which has support for base images as well as full-featured containers and integration with GitLab, validation test suites, and even cloud images. Here is an example of AWS image. We have a tutorial tomorrow on accelerating HPC using containers. Please come for that, and we'll be able to show you the use of E4S. I would like to thank our sponsors, DOE, DOD, NSF, NASA, CEA, and especially our industry partners, including AMD, ARM, Intel, NVIDIA, IBM for their support, and our partners at various institutions, including the Ohio State University, ParaTools, University of Tennessee, Knoxville, the developers of PAPI, TU Dresden in Germany, the developers of Vampire, and Hewlett Support Computing Center, the developers of Scorpy, and thank the Exascale Computing Project for their sponsorship of Tau as part of the Proteus Tune project. So any questions? Can Tau use Rock Profiler and Rock Tracer together? No, we use one or the other because both of them give us events such as when a kernel entry and exit execution takes place, and we have to coalesce the timestamps with the host timestamps to get a good trace file. So we use one or the other. We have features of HIP that can be exposed through the Rock Tracer interface. Can Tau perform load imbalance and communication overhead analysis for distributed memory codes using multiple GPUs within a node? Yes, we can do this. And you can see the load imbalance from a communication standpoint, and you can see exactly what it looks like. And I can work with you offline. I think we are just about out of time. John, is that right?
Just about. Happy to take a few more questions, though. So, question for me: do you have any concerns about scaling Tau for these large-scale systems in terms of the data collection or the data analysis?
So the max size that we have looked at so far is 786,000 MPI ranks so far, and our browser was able to handle it. Our 3D graphics worked properly. That's the max we have seen so far, but I don't see a problem with sufficient memory that it will be able to handle this. Now, I should mention that for a size of that kind, we don't recommend that you generate one profile file for each thread. We use the Tau profile format equals merged option. And for that case, it took about 48 seconds or so to merge the profile at the end of the execution. So it took an additional roughly a minute to coalesce the data from all the ranks into a single file.
John, another answer to your question as far as analysis, a profile that size requires a pretty beefy workstation to just load it to begin with.
Yes, I'm concerned just about how big things are going to grow. I know that if we're collecting, say, GPU traces, you can't control the frequency at which someone accesses the GPU. So we've seen as many as like hundreds of thousands of offloads per second, in a process.
Yep.
So right. So things are going to go pretty big. So we're concerned about managing things out of core.
Yes.
Like in our user interface and whatnot.
Yeah. In addition to that would be a library like Magma that spawns a new stream every time that you do a solve. And every stream since those streams can overlap with each other, each of those has asynchronous behavior. We treat them as virtual threads, which becomes a resource drain pretty quickly.
Mm-hmm.
And maybe Kevin, you can add your thoughts to this question about OpenMP profiling, whether it records the time to execute the OpenMP target region, as well as the actual time in the GPU kernel.
Yes, it does. And full disclosure, this support was added like a day or two ago. So it's pretty hot off the presses. What happens is you get a target region that happens on the CPU side, and then you also get a target event on the GPU side. And then you get a target submit event that actually represents the kernel execution. And then there's target data operations that do the data transfers to and from the GPU. Not sure if looks like you collected a lot of threads there. So down to the GPU there, those are still CPU threads, but yeah, so this is the GPU activity. If you select some of those, so there's compute targets. Yeah, that works. So the target submit is the actual kernel execution.
Yeah. And
And the name we get from it is whatever the compiler generated as the outlined region of code. And we tack on the line number from the file to help identify it.
so you can see this arrow going from the CPU thread 0 all the way to this GPU kernel in Perfecto. Well, if you have other questions, please feel free to reach out to us and we'll be happy to work with you and get your codes instrumented and help with the analysis. But I think we should move on to the next speaker.
Thank you, Samir and Kevin. All right, Heike, I guess you're going to start.
Yeah, I'm going to share. Okay, should share something. Let's see. Let's hide all those participants, and I should be able to click here. Can you see my slides?
Yes.
Full screen?
Yes.
Okay, excellent. I don't see them, but all right. So yes, so this is Heike Jagoda, and together with Anthony Donales, we are going to talk about some of our most recent PAPI developments for GPUs and CPUs, and you know, the associated challenges. So there are two parts to this talk. So I will give an update on GPU support, and Anthony will focus on updates for CPU support. So I'm not sure if everybody on that call knows what PAPI is all about. So just lightning speed, I'll give a very quick overview of what PAPI is. So let's start with a list of supported architectures we have for PAPI. So, and again, right, I'm not going over the entire list. So this is merely for reference to give you an overview where we are today. And so the items you see on that list, it's a very sparse list, on that particular slide. So those are only the supported CPUs for various vendors. So in here now, I'm adding the PAPI support that includes counters found on the latest GPUs, and that includes NVIDIA GPUs, AMD, and Intel GPUs. Now we have also support for different interconnects, including GPU to GPU connectivity, as well as I/O and file system support. We have power and energy monitoring and capping support. And again, not only for CPUs, but by now also some of the GPUs, specifically NVIDIA and AMD. We have ARM support, and PAPI works also in various virtual environments. Yes, so in addition to all the hardware events, we also added support for software-defined events in PAPI. So in summary, if you look at that complete list of our supported architectures, the primary job of PAPI, which is also a challenge that keeps on growing and growing, is to provide a single portability layer to all these different performance counters that are listed here. The CPUs, the GPUs from different vendors with different characteristics, different networks, power and energy readings. So the objective of PAPI providing a single interface, or as I mentioned, portability layer, is so that application scientists or any users of HPC systems or tool developers don't really have to necessarily fumble with 50 different ways to get access to performance metrics for the many different hardware components on heterogeneous systems. So for the first part of the talk, we'll cover just a small sample from our most recent PAPI support on GPUs. So we have broken it down into two different activities. So the first is pure performance counter monitoring at the core level of GPUs. And for that, PAPI has pretty much equivalent support across Intel, the AMD, and NVIDIA GPUs. More or less, the floating point counters are still in question for the AMD GPUs, but I'm curious to to get access to them from pressure from, from what you heard from the previous talk. And the second is our power monitoring and capping activity in PAPI. So here, as of today, we have support for AMD and NVIDIA GPUs finalized and shipped. And the support for Intel GPUs is currently something we're working on. So that's something to look forward to. And yes, so we will provide some more detailed update on these highlighted activities here. And okay, so I just want to briefly mention that a lot has changed in the PAPI ROCm component for AMD GPUs, specifically the latest PAPI ROCm component supports now both sampling and intercept monitoring capabilities. And one of our team members, Giuseppe, gave a talk on just that, covering all the PAPI ROCm related updates, which was part of the AMD tutorial that was presented on Monday. And so we are not going to repeat that here, but I would like to refer to that material. So here's a link to the slides, and I believe the session was also recorded. And then alternatively, there's also a poster session later today where there is an opportunity to chat about any of that. All right, so for the first activity, we have developed support for the latest monitoring features on the Intel GPUs. And this was done in very close collaboration with the Intel team early on. And similar to what Samir commented on in his talk, so vendors, AMD and Intel, have certainly made a strong effort to work more closely with us and also meet our requests, which has been fantastic. So shout out to the vendors, teams that work with us. So back to the Intel GPU component. So PAPI users can now monitor GPU counters and also memory performance on the Intel GPUs. And this work was finalized and released last fall, winter, sort of. And this PAPI component uses the Intel Level 0 interface, which allows for two different collection modes that are fairly distinct. So on one hand, we have the time-based collection mode, where counter values are aggregated and stored in a buffer and can be read at any given time during the execution, which means the performance counter monitoring is completely autonomous from the kernels that are running in the GPU. And then on the other hand, we have the kernel-based collection mode, where the monitoring is per kernel. And the performance counter data is not available during the kernel execution, but only after a kernel finishes. And in this mode, the Level 0 API uses internal barriers, which implies that if two kernels overlap, like it is the case on the left here, the execution of that second kernel gets pushed out until the first kernel finishes. So that is something to keep in mind when selecting the collection mode, which you can do just by setting an environment variable in PAPI. So both collection modes are successfully supported through PAPI. And so here are two little examples to demonstrate its usage. So the first example covers the kernel-based collection mode. So here we are running a simple GEM, matrix multiply computation that is repeated 4 times. And for kernel mode, the PAPI counter results are reported once the kernel finishes. So you have one set of counters that are reported. And now for the second example, we switch to time-based mode. And here, so in a separate thread, we call PAPI read every 200 milliseconds. And this enables users to get more frequent counter results while the kernel is executing on the device, or kernels if you have multiple running. So as opposed to only one counter value at the very end of the kernel execution, as that was the case for the previous mode. So these are really just examples to demonstrate the new PAPI capability. And certainly users can use PAPI directly, but our primary focus is on PAPI as a middleware. So for tools that want to use PAPI as a middleware, the continuous integration of hardware event support and also power monitoring support is very important to us. So in this example here, it demonstrates the use of PAPI from within tau, and the code executed, it's the same jam computation that was used on the previous two examples. And it shows that users are able to successfully monitor PAPI events on the Intel GPUs from within the tau profiler. All right, so moving on to our power monitoring activities in PAPI. So as mentioned previously, support for Intel GPUs is currently work in progress. So here we will concentrate on PAPI power support on the AMD GPU. And so our objective also for this activity is to provide access to similar monitoring capabilities for the three types of GPUs, NVIDIA, AMD, and Intel, so that users can monitor comparable events regardless of what the underlying GPU architecture is they're running on. So here we have developed power management support, which implies monitoring and capping of power for the latest AMD GPUs. And for this, we have released a separate PAPI component called ROCm-SMI that needs to be configured in when you build or install PAPI. And this component interfaces with the AMD system management interface. And again, the monitoring features are similar to what we already have for the NVIDIA GPUs. So we have monitoring support for power consumption, fan speed, temperature, and also power capping support. And the graph here shows just some power readings with PAPI for the AMD GPUs. And here we use a HIP-based matrix multiply kernel, similar to what we used in the previous examples, and just HIP-based, and collected some fine-grained power usage samples with PAPI read, where the power is monitored every, I believe, 10 milliseconds in that case. I didn't put it on the slide. And here we ran the same experiment, the HIP-based jam kernel on the same GPU, but instead of using PAPI directly, we use PAPI from within tau to monitor power usage on the AMD MI100. And here you can see that the same PAPI ROCm-SMI event was successfully monitored. So as mentioned before, we are currently developing a new PAPI power component for Intel GPUs. And that component will also have monitoring support for GPU temperature, memory temperature, power consumption, fan speed, and also setting power limits will be available. And once again, our objective, and also sometimes that's also a challenge, is to get equivalent monitoring support for all the three types of GPUs. So sometimes the challenge is to really find the right folks from different vendors to work with in order to make that happen and to get access to what we are requesting so that our users can compare similar events when running on different types of GPUs, which is not an uncommon request. So other features we are currently working on are performance counter support for Intel's GPU to GPU connectivity. And the goal here is to develop PAPI support for metrics that monitor events like how much data was transmitted, how much data was received, what's the throughput of transmitted data, and what's the throughput of received data. And these are just a few examples of interconnect-related monitoring features that are important to the HPC community. And then last but certainly not least, the PAPI support for Sapphire Rapids is also something we are currently working on with Intel. And so that concludes the first part of the talk. So I will stop sharing my slides so that Anthony can continue. And I think we are still good in time. So let's see how I do that. I should stop sharing. Yes. So Anthony, you should be able to take it from here. Other questions?
Okay, do you see my slides?
Yes.
Yes.
All right, so hi, I'm Anthony Donalis, and I will talk about our efforts to analyze native events, primarily on the CPUs with PAPI. So for doing this, we have a sub-project within PAPI that we call the Counter Analysis Toolkit, or CAT. And you can find that as part of the PAPI repo. When you download PAPI, CAT is part of it. The goal of this effort is to create a set of micro benchmarks that when you run them, the different behaviors that they exhibit illustrate different behaviors of the microarchitecture itself. And so the idea is, if the vendor claims that there is a new feature, but there is no, it doesn't have any effect on my code, then it's as if that feature doesn't exist, right? So inverting that argument, everything that I can detect, I care about, right? And the target audience for that is performance conscious developers that want to measure the performance of their code, but they don't know, for example, which counters to use to measure specific things. Also ourselves, when we try to create our preset events, the high-level events that PAPI provides that are not vendor-specific, but they are defined based on vendor-specific native events. And also developers that, or tool developers that are interested in validating events, because sometimes you measure something, the event claims that it measures one thing, and in reality, it measures something else, or it's completely broken. So this is an effort to help everybody that is interested in using hardware events to measure things. So how do we do that? Let me show you, let me start with some simple examples. So consider this microkernel here, and it's a little loop that has a branch in it, has an if statement. And this branch has known behavior by design, right? It will be taken 50% of the time because of the comparison there, and it's so simple it will never be mispredicted. Similarly, you can make similar claims for the branch that defines the end of the iteration of this loop. And then we have another kernel where the condition depends on a random variable, so it will be mispredicted 50% of the time because it's impossible to predict the last bit of a random variable, and it also will be taken 50% of the time. And we have yet more kernels that, again, by design, do things that are slightly different from one another. But the important thing is that we know in what ways they're different. And in some cases, you don't exactly know by looking at the C code in what ways they're different. For example, in this case, there is a loop, there's a branch, there is an if statement, but you don't know by looking at the C code if the compiler will generate code where the jump happens to jump to the if statement, or it happens to jump to the else statement, right? To skip over the if you invert the condition. But looking at the assembler, when we compile the benchmark in order to run it, we can easily identify where that is, and we can see that, well, in this particular case, the branch was so that it, for the else case, right? So it jumps over the if the invert condition is true. Why am I telling you this? Because this way now I know that on this hardware and on this compiler, I expect that this branch will execute 100% of the time, but it will never be taken because the else is what's taken, right? And the if is always true, so the else is never taken. Anyway, putting all this information together for all the different micro benchmarks we have, we can create a table where we say, for example, if I'm interested in all branches, then these are the numbers I expect to get from my different benchmarks. And if I'm interested in mispredicted branches, then these are the numbers I'm expecting to get from all the different benchmarks. And by putting different rows for the different concepts that relate to branches, I can create a full table. Now, after I have my table, I go to the actual hardware and I run my benchmarks against all possible native events, for example. Let's say I disregard the naming completely because I don't trust the names of the events, and I run across all the events. Now, if I run against an event that measures, let's say, cache misses, I'm going to get all zeros because these benchmarks don't do any data accessing. So these benchmarks are not sensitive to cache events, but they are giving me a different response for different branch-related events. And by matching this response, these actual measurements with the table that I told you before, that is my expectations, I can conclude what these different native events measure, even if their name is completely bizarre and undecipherable. Also, I can use that to do some sanity checking. Like I said before, I can check that the events measure correctly what I think they measure based on their names. For example, here, the purple line is conditional branches, and then the orange and black gray lines, respectively, are conditional taken and conditional non-taken. And if you add them up, you see that you get the total sum, which is great because, again, here I'm telling you success stories, but it's not always the case that all events work as advertised. So being able to do sanity checking is important for the events themselves, but also for our benchmarks, because nobody guaranteed that our benchmarks are perfect. So by seeing that they agree with what the vendor says across multiple vendors is a good confirmation that, you know, we know what we're doing. Moving on to the memory hierarchy, it's much trickier, and I'm not going to go over the details of what this slide is showing. The bottom line here is that we use a technique called pointer chasing. And what you do here is you create a buffer where you chain all elements. Each element is a pointer to another element. Okay, and you can take all the time in the world to create a perfectly random chain or chains with whatever attributes you want, because you don't measure that step. And then the step you actually measure, you start the measurement, and then you just dereference one after the other these pointers. You get from each array element the address of another array element. And this doesn't have any overhead, it just tortures the memory. Now, by running this benchmark multiple times with different buffer sizes, you get a response curve like this. This is from an Intel Ice Lake SP, and the x-axis shows the buffer size growing, and the y-axis shows the different access latency divided, so the total, you know, execution time divided by the number of accesses we made. And you see a nice step function. As soon as you exceed the line one, the L1 size, which you see the little vertical line there, suddenly you see a jump to another latency level, and then to another one. And then you don't see a clear jump from the L3 to memory because, you know, prefetching does a miracle job of hiding the fact that some of these memory access were not really to the cache. But then I can go back and I can modify all the parameters that affect the benchmark and make it harder for the prefetchers to guess. And if I do that and run it multiple times, then I can get a more complex curve. And what you see here, each region, each shaded region is pretty much the graph that I showed you before, the step function, where the x-axis shows you the buffer size growing. And then when you jump to the next shaded region, the benchmark starts all over again, the buffer size resets, but the parameters that define the access pattern change. And you see here the middle two, how they have higher access latencies because they have a more difficult to guess access pattern. And the last two have low because they're pretty much streaming. So it's trivial for the prefetcher to guess what I'm going to need next. Now, running this against all native events, I can see one event whose response is this. And that is obvious. Immediately, as soon as you look at it, you can tell that this measures L1 hits, because while the buffer fits in the L1, I get 100%. And while the buffer doesn't fit in the L1, then I get 0%. And again, when we go to the streaming axis, I get hits even when the buffer doesn't fit because the prefetcher manages to fetch things ahead of time. Complementary to L1 hits is L1 misses, that you see the exact opposite response. But then we go to, when you miss in the L1, what's going to happen? The access is going to go to the L2 as a read, right? And you see here an almost perfect match between L1 misses and L2 reads, which again, sanity checking as we go, because again, not everything is as rosy as I'm showing you here. But even here, you see some difference at the very right between the misses and the reads. And the explanation of that has something to do with the fact that one is demand data and the other is not. So it has to do with prefetching again. Going to the L2, the picture becomes more complicated because now, again, prefetching manages to give me a hit rate even when the buffer doesn't fit in the L2, actually doesn't even fit in the L3 on the very right edge of each segment that you see here. And still I'm getting L2 hits, but it doesn't really matter because the shape is unambiguous that, you know, there is nothing happening when the buffer is in the L1, then it's 100% of the event when it is in the L2, and then it drops significantly when it doesn't fit in the L2. Well, that sounds like L2 hits, right? And when you go to the L3, it seems much more complicated, although again, you see the bump when it is in the L3 or just outside the L3. And if you take into consideration what we measured for the L2, you know, because only the L2 misses will go to the L3 at all, you see again that you can explain these curves and you can match these curves, these responses to the behavior, the higher level behaviors that we're interested in. And again, bringing more data in from the L2, you can do further sanity checking that if you add hits and misses and whatnot, you get a sum of 1. And everything seems to work great. Now, unfortunately, not everything is great. And here is a measurement of the event called L2 lines out non-silent. Okay, this is a native event. And if you look at the response, trying to understand what that measures, it looks like L2 misses, right? Because while I am before smaller than the full size of the L2, I don't get any response. And then as soon as I exceed the size of the L2, I get full response. And then for the two middle regions, I even get twice as many, which sounds a little counterintuitive already. Like why do I access the memory once and I get 2 of those events? But in any case, it seems to be L2 misses. But if you read the description that you get either from PAPI Native Avail or from Intel's website, this event is supposed to measure modified cache lines that are written back to the L3. So when we first saw that, our first assumption was, oh, there must be something wrong with our benchmark. And somehow it's also causing writes. So again, we went to the assembler, and I don't expect the audience here to be experts in assembler, but this repeating line that is the heart of the benchmark does what the equivalent of the C code is dereference the pointer to give me the next address that I will just dereference in the line below. There are no writes. So why is this event telling me that as soon as my buffer exceeds the size of the L2, 100% of my accesses or 200% of my accesses cause a write back to the L3? I don't know. The answer is we still don't know. We have communicated that with Intel, and we still don't have an answer. So, and actually, this is a behavior that is not new to the Ice Lake SP. We had observed that with previous generations of processors as well. And it's still a mystery to us why that happens. But this is one of the cases where I said at the beginning, this effort is not only to discover, but it's also to validate. Okay, so this event doesn't measure what it claims to be measuring. Moving to AMD. So here you see a very clean step function. Okay, and this is L2 reads. Okay, and you see that as soon as the buffer, as long as the buffer fits in the L1, there are no L2 reads, as there shouldn't be. And then as soon as the buffer doesn't fit in the L1, all the accesses cause L2, or yeah, all the accesses cause L2 reads. But the catch here is the following. Our benchmarks are multi-threaded. This processor has 24 cores. And what I'm showing you here is among the 24 threads running this benchmark, this is the fastest response. This is the minimum number we got for each buffer size. Okay, so this is the best case scenario. If I show you the average among all threads, then it has a bump right there, right? And now, again, when you look at that, you think, wait a second, why is there a bump in L2 reads when the buffer size still fits in the L1? And the first thought we had here is that, again, just like in the case of Intel processor, this event is not really measuring what it claims to be measuring. But to verify further, we did an analysis, we looked at latency, because latency doesn't lie, right? Latency doesn't claim to be one thing and it turns out to be something else. Latency is time. So if you measure if you record the minimum latency, again, corresponding to the minimum, to the thread that got the fastest response, you get a nice clear step. But if you measure the average latency, and here I'm going to clean the graph by having only the two averages, you see a bump that perfectly matches the bump in L2 reads. And the scale now is not, so the latency graph is scaled just so that we can see them in both in the same graph. The values don't correspond to the y-axis values. But qualitatively, the two bumps perfectly match. And again, this is a microarchitectural, surprising behavior that we have communicated to the vendor. And I will second Samir here that we have a very frequent and very fruitful collaboration with AMD. And yet, for this particular problem here, we never got an answer. And despite having such a collaboration. So I can't imagine the frustration of an application developer who's trying to figure out what's going on here. So anyway, to summarize, modern CPUs have thousands of native events, and there is a lot of documentation about them, but the name and the description of these events in the documentation doesn't always match reality. And also, when there are problematic event behaviors in the microarchitecture, even communicating with the vendors doesn't always explain problems. So it's good to have a mechanism for detecting problems and hopefully explaining them. And our mechanism for doing that is benchmarks, because benchmarks produce useful responses for different events, and they can highlight problematic events and problematic behaviors. And there's a whole different chapter that I didn't touch at all, which is, doing the matching of these thousands of responses with thousands of expected curves is really a machine learning problem. But, we don't have time to go into this. So this concludes my talk, and I'll be happy to answer questions.
Anthony, this is John. So
yeah.
The unexplained behavior you had where you were seeing these writes back from L2, does the system that you were measuring it on have inclusive caches? Because if it doesn't, then you might need to write back from L2 to L3 just to keep the read-only data.
So that happens again, as I said, across generations, we have observed that, and some of them were inclusive and some of them were not. So that doesn't seem to be the explanation, but I can think about that a little harder.
That's the only explanation I can come up with.
So I don't see why. So if the data fits in the L3, so it's already in the L3, and the L2 is accessing it to read it, when it doesn't need it anymore, why does it need to be written back to the L3?
So for instance, in the power architecture, there are multiple modes in the cache where either you can migrate the data from a lower level cache, from say L3 into L2, and then evict it from L3 so that your only copy is in L2.
Oh, I see what you're saying. Yes, but if the data fits perfectly in the L3, why would it need to be evicted from the L3?
Well, it gives you effectively more
because it's non-inclusive. I see. Yes.
Because you don't have because you don't have duplicates.
Yes.
Okay,
yes.
that's the reason why people made non-inclusive caches in the past.
Okay, I have to double check. I'm fairly confident that we observed that in the Cascade Lake, in older generations that were inclusive, but I have to cross-check it.
Okay, that's not a criticism of your talk. I find the counter names completely mysterious myself. And so I think being able to sort of try and figure out what they are is a really valuable thing.
Okay, thank you. Okay, I'm going to stop my share.
Other questions for Heike or Anthony? be shy. Okay, then I will get my slides set up. And if you think of a question while I'm doing that, feel free to ask it. Everyone see my slides?
Yes.
Yes, we can.
Thank you. Okay. So in the last talk in this session, I wanted to tell you a bit about where we stand with HPCToolkit for the Exascale systems. So briefly, the HPCToolkit project is a collaboration between Rice University and the University of Wisconsin. So Rice is working on HPCToolkit, but one of the things that we depend heavily upon the University of Wisconsin for is the Dynance binary analysis toolkit. We use the Dynance toolkit to analyze CPU and GPU binaries and obtain all of the information about inline code, line mappings from the symbol table, and also to analyze control flow of CPU and GPU code. And so the goal of our project is to develop effective tools to measure, analyze, and understand the performance of basically the entire software stack. So not just applications, but also runtime libraries and our own tools included. And then we've been working with the vendors on helping them figure out how to refine their hardware and software ecosystems to enable better tools. So in order to prepare HPCToolkit for Exascale platforms, we've added support for measurement and analysis of GPU accelerated code, as others have described. And so inside HPCToolkit, we've built a GPU independent layer for measuring and attributing GPU operations. And so this is something to just sort of simplify our own lives so that we could take the information from different GPUs and sort of fit it into a common framework that we use to measure and attribute performance. We have a GPU independent tracing layer, and we also have some GPU, so we have some GPU dependent measurement subsystems. And so the software stack that is doing the measurement for the GPUs is all provided by the vendor. And so we have coarse grain measurement support from AMD, Intel, and NVIDIA GPUs. And so by coarse grain measurement, what I mean is timing individual operations, such as data copies, the amount of time spent in executing GPU kernels, that sort of thing. The other thing that we're actually measuring and attributing with HPCToolkit as well is fine grain measurement within GPU kernels. And so we're using both sampling. So sampling, we're doing PC sampling inside the GPU on NVIDIA GPUs, and we're currently using instrumentation on Intel GPUs to gather some fine grain instruction level information. So another thing that we've been building out for the ECP project is some scalable postmortem analysis of extreme scale performance measurements. So one of the questions I asked during Samir's talk is just, what about the data? And so the data is gathered pretty quickly when we're looking at things at scale. And so we don't actually aggregate our data at the end of a measurement step. Samir talked about doing that immediately at the end of the execution. We take our performance data and we overlay it with additional information to allow us to relate it to inline code. And also we analyze the GPU binaries that were revealed during execution. And so we do that in a postmortem analysis step. And so we've built out some support for scalable postmortem analysis of our performance measurements. And then finally, inside HPCToolkit, we've built some support using the OMPT interface for OpenMP to monitor OpenMP offloading. And I'll tell you a little bit about where we stand with various vendors in a minute. And so I also mentioned that we're closely partnered with the Dynance team at the University of Wisconsin. So we're using Dynance to support analysis of GPU binaries by parsing AMD GPU binaries. They parse the machine instructions, And then while Dynance doesn't directly parse Intel binaries or NVIDIA GPU binaries inside HPCToolkit, we inject some information about the basic blocks and the instructions that are present, and we use Dynance to do loop analysis of control flow analysis of the GPU binaries, and also to process information about the symbol table. So the way HPCToolkit sort of fits together with the GPU software stacks is for the different vendors, we have the 3 different kinds of GPU at the bottom, and we have HPCToolkit as our GPU independent measurement substrate. And then this supports sort of a full software stack on top of it. And so on NVIDIA GPUs, we have, say, Cocos and Raja, and Cocos and Raja can certainly be run on top of CUDA. I think they can also work on top of OpenMP. OpenMP is built on top of CUDA. And then we also have direct support for OpenCL as well. On Intel GPUs, we have Cocos and Raja built on top of DPC++. And OpenMP is atop OpenCL or level 0. And then on AMD GPUs, we also have Cocos, Raja's OpenMP. And then there's the HIP layer that is the common user level programming layer. And then there's also HSA, which is the underlying implementation layer for HIP. And then the OpenMP is generating code directly for HSA. And so we're using the CUPTI library from NVIDIA, we're using the rock tracer library from AMD, and we're using intercept. So we're intercepting calls to level 0 and OpenCL on Intel GPUs. And then for instrumenting code, we're using Intel's GTPin. This is for instrumenting GPU code, and we're using the Sanitizer API from NVIDIA. So let me show you a little bit about our workflow, and I'll show you what we've been working on for the ECP project and show you some of the results we have, and then tell you about some of the things that are still work in progress. So in general, you compile and link your programs without any changes to your makefile. The only thing you might want to do is add a -G to your builds so that the compilers will record some line mapping and inlining information in your generated binaries. And you can add -G in addition to optimization. And so you'll just generate your optimized binaries the way you normally do. And then we profile it using HPC run, and we'll collect profiles and traces. And so these are profiles of activity on the CPU, as well as profiles of the functions on the GPU associating time and hardware counter information with GPU kernels, and then tracing on the CPU and GPU. And so in order to use this to profile on the GPU, you'll just say HPC run, and you specify GPU is equal to XXX, where that XXX might be NVIDIA, AMD, OpenCL, or level 0. So when we started, it was just NVIDIA and AMD. Maybe this should be changed to CUDA and ROCm, but since we have OpenCL and level 0, but this is what it is today. On Intel GPUs, we can also, you can say, like, I want to do GPU level 0, inst, and this is going to do instrumentation of the GPU kernels. And this will allow us to gather instruction level information. On NVIDIA, we can do PC sampling. And so you'll add a PC. You can add it or not. On AMD GPUs, we also have support for using the OpenMP offloading interface to monitor performance of OpenMP offload on the GPUs. And so you can get that by saying GPU is equal to OpenMP. And the things that I've shown you here can be combined with, say, using timer-based sampling on the CPU, or there's a wide range of hardware performance counters where you can specify the name of a hardware performance counter. And so you can get a complete list of the things that you can use to sample on the CPU, or counters that you can use to measure on the GPU by just saying HPC run-L to list all of the available events. And then HPC run composes with job launchers. And so you can, on LSF, you can say JS run and launch something, and then you say HPC run GPU with the monitoring specification in your application, the same sort of thing with S run or AP run. So what HPCToolkit does is it aggregates profiles on the fly. So we're collecting a calling context tree per thread, and also for a GPU stream. And this calling context tree includes not just like call chains. At the leaves of the call chains are actually measurements for individual machine instructions. And so we can associate measurements with individual machine instructions in your application. And so we're also collecting CPU traces. Our traces are not in anything like OTF format that Samir was describing. We're using a custom tracing format that is very compact. And so for our CPU traces, we're tracing actually call stack samples, and each individual item in the trace is only 12 bytes. And so it's very compact. For GPU traces, we're tracing call stacks that initiate GPU operations. So you can see the GPU operation that's being initiated in its calling context, and that has that's only 24 bytes. So to measure on these GPU accelerated platforms, we have the CPU hardware performance monitoring unit that can measure all sorts of things like the branches and cache misses like Anthony was talking about. On the GPU, we have hardware counters, and on NVIDIA GPUs, we have support for PC sampling within the kernels. There's a collection of software that's involved, and so it's worth mentioning the collection of software because there's problems with each of the layers. And so for glibc, we use the LD audit for tracking dynamic loading of shared libraries and binding of symbols. Ran into a great many problems with that, and submitted a 20-page document to Red Hat, and have been working with them closely to try and address some of the issues. And so they have a new version of glibc out with fixes for this that we very much want to see on the ECP platforms. We're using Linux perf events for monitoring the CPU hardware counters. We're using the GPU monitoring libraries like HpCT, Rock Tracer, Rock Profiler. We're using GPU intercept libraries for OpenCL and level 0, and instrumentation for fine-grained measurement. And so the measurement modalities, we have sampling on the CPU, we have callbacks or intercepts before and after GPU operations are launched, and sometimes when they're completed, like we get completion events on level 0 and in OpenCL. And then there's a GPU event stream for GPU operations from HpCT and Rock Tracer. And the event stream for NVIDIA GPUs also includes PC sampling information. So that's what we're doing for measurement. And then once we have this measurement data, we have information recorded where measurements are made for, say, individual machine instructions or individual kernels, GPU kernels, or individual instructions inside GPU kernels. And now we have to relate all of that back to source code. And so the tool that we use to do that is we have a tool called Hpc Struct. And so this does binary analysis, and it recovers information about program structure, how the machine instructions map back to functions, source lines, inline code. Was there a question? No. Okay. Is there a question? No, I guess it's making some noise as people are leaving. So what Hpc Struct does is you say Hpc Struct on the measurement directory, and then all of the CPU and GPU binaries that your application touched are analyzed. And so we analyze all of them in parallel. And so for small binaries, we generally analyze them with 2 threads. For large binaries, we generally analyze them with 16 threads. There are a couple of knobs that you can use to change the defaults, but in general, we're analyzing things in parallel to do it more quickly, and then we're caching the analysis results to reuse them the next time you run your program. Many of the things, like all the system libraries and things like that that you've touched, and many of your GPU binaries are all the same. And so we just reuse the results. So just to show you what we've been working on as part of the ECP project, we've been trying to make this binary analysis very fast. And so to speed it up, we use parallelism. And so one of the benchmarks that we use is analyzing the TensorFlow library. So this is a large library for, this is of CPU code. And so it's 7.7 gigabytes, and it's 170 megabytes of text and a whole lot of symbol information. And so what this is showing is, in fact, this is using HPCToolkit's graphical user interface HPC viewer showing traces. And so each of these is a trace line for an individual thread. And the fact that there's multiple threads that are doing stuff. And so each of these colors indicates exactly what activity is happening. And so you can see that this is highly parallel, this is highly parallel, this is highly parallel, and a couple of more serialized sections. But the takeaway from it is that we're analyzing this 7.7 gigabyte binary using 32 threads in 77 seconds. And so when we were doing this serially, this would take quite a bit longer. Think 32 times this, almost that. So instead of a half hour, we're doing it in a little over a minute. So once we have our profile data and our trace data and our program structure information, then we have a tool HPCProf or HPCProf MPI that that collates the measurement data with the program structure information so that we can render, we can associate your performance measurements with the source code. So we've been working on building a new version of our postmortem analysis tool, HPCProf and HPCProf MPI, that analyzes profiles and traces using a technique that we call streaming aggregation. And so previously, for analyzing large-scale performance data, we would launch an MPI job, and each of the MPI ranks would pick up a collection of profile files and aggregate them together, and then there'd be some communication among the MPI ranks, and then it would write out all of the data. And so now what we're doing is we added multi-threading within the MPI ranks, and we found that it scales much better by using the threading. And so we take the data from the profiles and we stream them through and record everything we combine a bunch of profiles into concurrent shared data structures, and then we print out the aggregated results when we're done. And so what this enables us to do is we were looking at some large scale experiments. And so measuring 2K MPI ranks and 2K GPUs, we were analyzing the data using 63 threads on a node, 504 threads on 8 nodes, or 1,008 threads on 16 nodes. So this is using 63 threads per node. We were able to bring the time down from 14 minutes for analyzing 75 gigabytes of data down to just a minute for analyzing the performance data. So there's a couple of things that are going on here. One is that we're using highly multi-threaded parallelism, and the second is that we switched from using a dense format for recording our measurement data to using a sparse format. So the second thing is that we're using minimal resources for doing this. So instead of doing our analysis at the full scale of your executions, we're just using somewhere between 1 and 8 nodes and analyzing gigabytes of data on the order of a minute. And an important thing was that this reduced the memory footprint of HPCProf. So instead of trying to load up all of the cores in a node with an MPI rank, and every MPI rank has independent copies of the data structures that it's aggregating, that had a large memory footprint, and often we would have to reduce by 4x or by 16x. So like using only 1/4 of the cores or using only 1/16 of the cores. With this multi-threaded approach, in fact, we can do it and load up all the cores and analyze the data much faster and not run out of memory. And so for analyzing the ECP Pele-C application running on 2K MPI ranks and 2K GPUs, instead of 41 minutes using the current HPCToolkit, which is using a dense representation for CPU and GPU metrics. And a dense representation is bad for heterogeneous programs because we have effectively slots for all the GPU metrics for every CPU context, which is madness. And so we replace that with a sparse approach, and we got a factor of 40 reduction in the analysis time. So this is something that's unreleased in our develop branch, and this is going to be in our next release. So this shows using our viewer, this is showing a run of the analysis of the streaming aggregation. So the important point is that the streaming aggregation approach is showing like very large scale parallelism. And the fact that there's all these flecks of color means that basically we're keeping all of the nodes busy. And so there's a reduction phase using MPI reductions in the front and then also in the rear of the analysis. And we could work on making these a little bit better, but in fact, the fact that we're analyzing the gigabytes of data in 41 seconds, we were happy that we got the bulk of the analysis parallelized very well. And I don't think we're going to invest more effort in trying to make this ideally parallel. So then the last thing is HPC Viewer is the user interface. And now I'll show you some of the performance data that we're able to collect with HPCToolkit. So in our user interface, we have a navigation view, some metrics. And so in this case, we have metrics like GPU instructions. We're actually using the PC sampling inside the NVIDIA GPUs. And so what we have here is a calling context that starts on the CPU, and then there's a little tag that we put in that says now we're transitioning into the GPU, and then we actually have calling context and loop information inside a GPU kernel. And so the interesting thing here is we found that for line 446, which is this loop, we found that there were 9.4% of the GPU stalls in the entire program were on line 446. Now I mentioned that we're doing loop analysis inside the GPUs. In fact, it says that there's a loop on line 446, but this is associated with line 446 outside the loop. And so initially we were pretty puzzled. And we also found that these stalls were mostly memory stalls. Well, when we looked a little closer, what we found was that using lambda capture, like lambda capture was used to pass this UData structure into the GPU kernel. And then the UData is dereferenced inside the kernel. And so we looked at this, and in fact, the memory latency that's exposed here is dereferencing this element in the UData structure. And so we're able to identify that by seeing these stalls that were attributed outside the loop. So what we did is instead of passing this structure, we passed UData components as scalars, and simply fixing the way that it did this lambda capture gave us a 4% speed up of the entire program. And so the thing that I wanted to show off is that we're collecting detailed data inside the GPU kernels that enables you to identify inefficiencies. And so this wasn't the only inefficiency that we identified with PayLacy. There were a couple of pull requests that involved optimizations that the PayLacy team was able to identify the need for. So we also show GPU traces. And so these traces are showing a CPU trace line. There's an MPI helper thread, and all of these little flecks are kernels that are executing on streams on the GPU. And so from this heterogeneous trace, you can see that the traces at the bottom have a lot less flex. In fact, there's GPU load imbalance that you can see visually here, where there's lots of flex on the GPU here and many fewer at the bottom. And so this is an indication that there's load imbalance across the MPI ranks. So the tracing, scaling the tracing is a challenge. This is showing that we can scale the tracing. This trace shows 512 ranks and 512 GPUs. We have trace lines for each of the streams on the GPUs and also for the 512 ranks and any threads within the rank. And so this is just showing a very tiny section. But if you zoom in, there's a lot of detail here, and you can look at the load imbalance and any sort of serialization that's happening inside your execution by looking at this in detail. And then for the place where there's the crosshair here, you can select any point in time across the trace, and what it'll show you is a full calling context for what's going on. And so this shows is going through lamps, going through Cocos, launching something using CUDA, and then there's a procedure that's happening on the GPU. And in this case, the procedure, information wasn't provided to resolve this to a name, but in other cases, I'll show you that we do resolve these things on the GPU into names. So for AMD GPUs, we can collect profiles and traces of HIP accelerated applications, such as capturing kernel execution, memory copies, memset, things like that, and attribute those back to the CPU calling context in which they're initiated, and show these source code oriented views and also the trace oriented views. So we can do this across multiple MPI ranks across multiple nodes. We have some new work with AMD. Samir mentioned the OMPT interface. So this is something that we work closely with AMD on, and we added support for the OMPT interface to track to track kernels that were offloaded onto the GPUs. And so it's the kernels and the data copies. And so in compiling things with ROCm 5.1 and AMD Clang++, we can attribute OpenMP computations offloaded to the full calling context. So in this case, we can see that there's an OMPT copy out operation, and that's attributed back to this OMP target update from a particular data object. So this shows that 70% of the time for GPU operations in total is a copy out that's associated with this particular update from in mini-QMC. So this is what our trace view looks like. And so we have the CPU, there were 96 threads on the CPU. There was a helper thread that was in AMD's toolchain that was monitoring the GPU. And right now we've collapsed all of the OMPT trace activities onto a single trace line. That's not right. I asked Kevin what they were doing. Right now, there's nothing in the OMPT information that comes back that indicates what stream it's associated with. And Kevin said that they're associating the trace line for every individual CPU thread. They're naming a synthetic GPU stream. So in fact, the events here overlap in time. And so we're jamming them into a single trace line. And so this needs to be replaced with something else. And so we're going to assemble a set of virtual trace lines, whether you use one per thread or just a sufficient number of virtual trace lines to resolve all the overlapping activities. That's something that we'll decide as we go along. So also, we can collect profiles and traces of DPC++ codes atop either OpenCL or level 0. So the same sort of thing, capturing information about kernel execution, memory copies, memset. And so this is showing a trace line on the CPU. So this was done on a single Gen 9 GPU integrated in a Skylake. And so we have one trace line for the CPU thread, and then we have the trace line for the GPU thread. And for the GPU, we can see that the full calling context. And so this is attributing it back to a Amrex parallel 4 operation in the calling context in which it was invoked. And so that's the single most expensive thing in the trace. Now on the CPU side, what we're able to do is we have heterogeneous calling contexts. And so you can see there's on the CPU, there's some Amrex operations, PC compute hypermolecular flux. There's some loops, some parallel 4s that are being launched through Amrex, goes down through the sickle layer. And then we see the GPU kernel at the bottom. Now the detail in the sickle here kind of gets in the way. So we can collapse that by pulling up our filtering interface and say, I just want to filter out all the lines that say sickle detail, because those are just details that they're implementation details that don't really matter. So we can collapse that down. And now that we've done that, we can see a little bit more detail of what we have at the lowest level. And so inside the implementation of an offloaded Lambda function for through the parallel 4 interface, we can in fact see the functions that it's calling on the GPU, and we have GPU instruction counts associated with the individual statements inside the function calls. How do we do this? Well, we're gathering flat information out of the GPU. We're not actually gathering calling context, but by analyzing the GPU binaries and recovering the static call graph, in fact, we know that if you're inside a function RPY2CS, it's either called in one place or in multiple places. If it's called in multiple places, then we just divide up the cost among the multiple call sites, assuming that the call sites are the same. That's the best that we can do. This is an assumption that's been made for years by gprof, and we're just extending that to GPUs. But what it can do is it can show you some detail of the calling structure inside your kernels and give you a little bit better handle of where the performance came from than just associating the cost with the kernels themselves. So finally, let me finish with a few concerns. So I mentioned that measuring these GPU accelerated applications on supercomputers is difficult. Well, so HPCToolkit is thread aware. Well, lots of threads get created. There's application threads, GPU runtime threads, tool support threads, tool threads. Which ones are we supposed to be monitoring? Right now is kind of an ad hoc thing. We've determined which ones need to be monitored with for each of the different vendor stacks. If they change their stacks, then there's going to be changes to the threads. This is not sustainable. Something has to be done about this. There has to be some sort of standard where the threads announce themselves, or we can interrogate the threads at runtime and say, what should we do with it? What's your role, and should we be monitoring it or not? Also, I mentioned there's different GPU runtime measurement substrates for the different vendors. There are cases where things like the Intel DNN library launches operations using level 0 functions that are obtained with dlopen dlsim. And so by trying to intercept the level 0 operations, we miss observing what's going on with this library. And so in order to avoid these sorts of blind spots, we've been using the LD audit layer. But there were lots of bugs in it that got fixed recently in glibc 235. Now, the problem is that we need to get this on the ECP platforms. And so this is in upstream glibc, which then needs to be integrated into SUSE, which then needs to be integrated into Cray OS. And so we're engaging HPE to try and do that. Also, currently only NVIDIA GPUs support PC sampling for instruction level performance measurement. So for Frontier, there's no support for fine-grained performance measurement. So on this slide, though, I show that this is a figure from AMD's Radeon GPU profiler for Vulkan, where in fact, for GPUs, they actually are able to attribute performance information at the line level and show that you spend time waiting for memory references to be satisfied, and that you spent 394 clocks here. And so they have this capability, but they have for the graphics stack and not for the ROCm stack. So at the moment for Frontier, we're kind of blind inside the kernels. And so I see that as a problem. Some other concerns at present, we have some open issues with ROCm, ROC Profiler, and ROC Tracer, that sampling using real time on the CPU causes ROCm to deadlock. ROC Prof, we've seen deadlocks using ROC Tracer to monitor a couple of ECP applications. So we know that this is not an issue with HPCToolkit, it's an issue with the underlying measurement infrastructure. And so while we can use HPCToolkit on these systems, we're not confident that it's not going to deadlock because there are issues with the underlying infrastructure. When using ROC Profiler and ROC Tracer together, the timestamps for the first kernel application are suspect. This might be due to a firmware issue with the GPUs, and we're investigating this right now with AMD. The timing information that comes out of the OMPT interface for AMD GPUs is suspect. So for 140-second execution, it's reporting 11,000 seconds of GPU memory copies. So it's probably reporting the timestamp. It's gathering the timestamp when it's submitted to the GPU, and then the timestamp when it finishes. And what we would like to see is the time that's actually executing on the GPU, not the duration between submitted and finished. We had a discussion about the hardware counters for Rock Profiler, and that situation is changing. As Timur said, AMD has now released the support for the additional GPU counters. There's a bunch of development challenges, and so we were finding that it's difficult to develop our tools. For instance, Intel GTPin 219 has bugs that make it unusable with Pele-C. There's an NDA version that works better, and so there are differences between the public and the private software stacks that cause us some difficulty. And also this the fact that LD Audit does not work well on any of the current systems, and that we need to wait for the new version from Red Hat is something that's sort of a constant source of irritation. So finally, just to summarize, so for NVIDIA GPUs, we can collect heterogeneous profiles, including instruction level execution and stalls using PC sampling. We can collect traces. For AMD, we can collect both the heterogeneous profiles and the traces, but we don't have any GPU instruction level measurements within the kernels. For Intel, we can collect heterogeneous profiles. We can collect instruction level information with kernel instrumentation. The support for OpenMP offloading seems to work a little bit differently than what we've seen with DPC++. And so there's a little bit work that we need to do in order to monitor that. And so I'll finish here. I'd be happy to take any questions.
John, you briefly touched on the problem of identifying which threads are interesting and useful to the user.
Yes.
When you filter out the ones that you know aren't useful, are you just doing it based on what libraries they happen to, what the library those addresses resolve to, or?
Yes, basically like CUPTI creates some threads in order to monitor the GPU. Yep. And so we just said, if the thread is created by the CUPTI library, then we don't want to see it because it only exists for performance measurement, and therefore it's not part of the application program. And so we shouldn't be reporting its performance as part of the application program. But that's something that like we kind of reverse engineered their library and decided what to do. Instead, there should be some way where they tell us this is a thread that is a tool support thread. And therefore, then based on that, a tool should say, well, then I shouldn't be monitoring tool support threads.
Are you intercepting the pthread create call, or just the first time you get a sample in that thread? I mean,
we are intercepting the pthread create call to say at the beginning of a thread, is this one that we want to monitor or not? In fact, with Rockham, there's a thread that gets created early on in the initialization of Rockham, and if we try to turn on our monitoring subsystem and try to initialize PAPI at that point, it'll deadlock because it's holding locks. And so we've learned that that's not a thread that we can monitor. And I just think that reverse engineering every vendor's runtime is madness.
Yeah,
we have to have some sort of standard.
Yeah, but I don't know. I mean, it's hard because everything resolves down to pthread create at some point.
Well, yes, but if we could interrogate, if we could develop an API where we could ask a library what or the library would sort of like, publish something, you could register for a call that says, okay, let me know before you create a thread what you're going to do, like what's it about? And then we could decide what to do, how to handle the subsequent pthread create.
Mm-hmm.
Hey, John, you have a couple of questions in the chat, so I'll read them off for you.
Thank you.
Does this tool support deep learning frameworks?
So we have some support for deep learning frameworks in a separate branch of this. It's not yet integrated. So this is work that was done over the last couple of weeks by my PhD student who is actually graduating on Saturday. And so I'm hoping to meet with him later this afternoon to figure out how we can integrate that into our mainline code. Excellent question.
Cool. So one more question in the chat. How much overhead does PC sampling suffer from on NVIDIA GPUs? Is there an argument against it, or should we expect the other vendors to adopt it over time?
So originally, back in 2017, when AMD initially released support for PC sampling, it made the applications run about 40x slower. And the reason for that had little to do with the PC samples that were being collected in the GPUs. It had everything to do with the way that NVIDIA had put together their software stack. And so we've been working with them over the last several years, and now they have a low-cost PC sampling that just costs maybe somewhere around 1 to 3% for the basic infrastructure for PC sampling. And so what they did is they got rid of all of the support that they had for attributing PC samples back to functions and source lines and things like that on the fly. Like every time you got a PC sample, it didn't need to be correlated with the source code. And so now using this lightweight framework, when we integrate that into HPCToolkit, it makes the application run about 2x slower, but 2x is really about the same cost that you pay if you're using, say, Nsight systems. Just monitoring all of the GPU kernel launches is the thing that seems to be the biggest bottleneck. The PC sampling itself is lightweight. And so I can say that Intel has said that they would be adding support for fine-grained performance measurement in a future generation of their GPUs. And for AMD, I can say that we've looked through their GitHub and we've found support for PC sampling in their commits on GitHub. So you can draw your own conclusions from that. The other questions? Going once. All right, then. I'd like to thank everybody who showed up, and especially those of you who asked questions. All of us would be happy to take questions from you offline, so feel free to track us all down by email. And in the case of HPCToolkit, the capabilities are emerging, and so we're looking to work with the platform staff to make sure that there are versions that are distributed on the ECP test beds. So you should see some of these available to you soon.
That's a really good question, John. Is HPCToolkit installed as a module on Crusher, or is there a path forward for getting that done?
So there is not yet a module for HPCToolkit on Crusher. Things work well enough with ROCm 4.1, with ROCm 5.1 that there should be. And so we'll coordinate with the ORNL staff to install it from SPAC.
Cool, thanks.
And Ayush, we're certainly interested in collaboration. Feel free to contact me by email, or feel free to contact whatever of the panelists here you're interested in collaborating with.